So this is Theorem 5 in the Euclidean geometry series, and it's dealing with cyclic quadrilaterals. So as mentioned before, a cyclic quadrilateral is a quadrilateral where all the vertices, all the points lie on the circumference of the circle. So you can see that's happening here. We've got A, B, C, and D all on the circumference of the circle. Now you're going to learn there's different properties of cyclic quadrilaterals. As I mentioned before, one of them is that the opposite angles add up to 180. So that we call that supplementary angles. Okay, so that's what we're going to prove in this theorem, is that the opposite angles add up to 180. There's also a converse theorem, as well as I can never say this word properly, but corollary of this theorem as well. The converse being that if you can prove that the opposite angles are supplementary, they make 180, then the quadrilateral is cyclic. So it's the reverse. Remember, converse is always the opposite. So instead of us saying, okay, this is a cyclic quadrilateral, therefore the opposite angles are 180, it's now, okay, so we can prove the opposite angles are 180, therefore this quadrilateral must be cyclic. Okay, then the corollary of this, I'll show you on a different, actually I'll show you after this. Let's first prove it and then I'll show you what the corollary is. Alright, so we are now trying to prove that the opposite angles are supplementary. Okay, so we're going to play around with some of the previous theorems that you've learned. So remember, just to start by saying RTP, that A plus C is 180 and B plus D is 180. Okay, so they say join or construct AO and CO. So by the way, if you are asked in an exam to prove any of these, you'll have to do that step and you'll have to say construct by joining AO and OC. Okay, so the first thing that we're going to look at is our theorem about angles at the center and angles at the circumference. I mean, it makes sense. We've just joined this so that we can have angle O1 and O2. So, do you agree with me that angle O1 is 2 times the size of which angle? Of angle B. Okay, so it's 2 times angle B, because angle at center is 2 times angle at circumference. Correct? Okay. Then angle O2, I mean, you can guess, angle O2, this one is going to be 2 times the size of which angle? Of angle D. So it's 2 times angle D. Again, angle at center equals 2 angle at circumference. Alright. But what do we also know about this angle O? What is this whole thing here? That whole thing is a revolution. What do you know about revolutions? They add up to 360. So, angle O1 plus angle O2 must be 360, because a revolution is 360. Okay, I'm sure you can guess now where we're going with this proof. We have already shown that O1 is 2b and O2 is 2d. So we can replace it. We can therefore say 2b instead of O1 plus 2d is equal to 360. So now if we factorize this, we take out the 2, we get b plus d is 360. So therefore, if I divide both sides by 2, b plus d is 360 divided by 2, which is 180. Do you see that we have proved that b plus d is 180, and that's what we were trying to prove? So you can go and do the exact same thing for A and C by connecting B and connecting D and then doing the same thing over, but you can just say, you know, by the same respect, A plus D is equal to 180. Yeah. or you can even go and do, I was just looking at what they've said here. They've also said the interior angles of a quad is the sum to 360. So you could even say that because these two make up 180, you can say therefore A plus C also equals 180 because interior angles of a quad make 360. That makes sense because all of these plus together, doesn't matter which quadrilateral you're in, they always add up to 360. So if you've already got 180, the rest must be 180 because it makes 360 in total. Okay, so that makes sense. Now remember, you always need a reason. So when we use this, our reason is going, what is our reason going to be? Opposite angles of a cyclic quad. Okay, now remember, like I said, there's a converse to this. So if you want to use it to prove that this is a cyclic quadrilateral, you could prove that the two opposite angles equal 180 and then say opposite angles are supplementary, therefore this must be a cyclic quad. But I am going to come to that. Okay, then the corollary, I've got it here. The corollary is one more property of this, and that is that the exterior angle is equal to the interior opposite. So essentially what they're saying is that if this is 110, the interior opposite is S. So X is also 110. The exterior angle is equal to the interior opposite. And if you are using this, your reason is exterior angles of a cyclic quad. Okay. Exterior angles of a cyclic quad. That is a reason, and you're allowed to use that. Okay. So let us now actually look at proving that something is a cyclic quadrilateral. We've heard a lot about it. Now let's just go through the 3 ways that we are able to do this. Okay, so remember, I'm going to write it here. A cyclic quad, right? What is it? Okay, all the vertices or all the corners are on the circumference. Okay, we've established that. The corners are on the circumference. Alright, we've also established that the opposite angles are supplementary. If a quadrilateral is cyclic, it means the opposite angles add up to 180. They are supplementary. We've also now just learned that the exterior angle equals the interior opposite angle. Okay, so if I go and show that the exterior angle equals the interior opposite, it must be a cyclic quadrilateral. And lastly, you may recall in one of the previous videos, we spoke about the angle being subtended. So if you look here, if you can show that x and y are equal, then it must be a cyclic quadrilateral. So you can say subtends equal angles or angle in same segment. Okay, so these 4 things are properties of cyclic quadrilaterals. Okay, so you can use them to prove that something is a cyclic quadrilateral. Okay, so I'm just going to run through one more time these 3 reasons. The first one that they give you is that x plus y is 180. So if I can show this x plus that y is 180, then I can say therefore this is a cyclic quadrilateral, and the reason being opposite angles are supplementary. Okay, the second one, the exterior angle, so this y is equal to that x, and if you want to use that to prove that it is a cyclic quadrilateral, you're going to say exterior angle equals interior opposite angle, therefore it is cyclic. And lastly, if you're using the subtending one, if you can prove that x and y are equal, so it's both being subtended from D and C, then it is a cyclic quadrilateral. So if you're going to use this, then you're going to say chord subtends equal angles, or equal angles of subtended, or angles in the same segment. You can use this as well. So if you use one of these three, you can prove that a quadrilateral is cyclic. Okay, now I'm going to do an example using Theorem 5 and then an example where I prove that something is a cyclic quadrilateral. Okay, so this is an example where we will be able to use this, and just remember, this Theorem 5 is about the fact that the opposite angles add up to 180. Okay, so let's look at it. It says ABCD is a cyclic quadrilateral and AOD is a diameter. Determine X and Y if O1 is 120. So I wrote it in here for you. There's O1 120. Remember, this whole angle O would make a full revolution. So just kind of keep in mind that this will be 360 degrees. Also, bear in mind that you've got this as a diameter. You've got a diameter going on there, so you might want to double check that there's no 90-degree angle that's subtended. I don't see any, but you know, it's always a good thing to keep in mind. Yeah, so whenever you're dealing with the center angle, a nice one is to look out for those early theorems that you learned. So in other words, angle at center and angle at circumference. I do notice that Y and O2 go together. This O2 pairs up with this Y. Okay, so remember, it was that reflex one. It looks a bit weird. It's almost as though if you were to draw another one, if I were to, you know, connect this to the circumference, then this one and that angle would go together. Therefore, this angle and this angle must go together. So O2 is double the size of Y, but we don't know what O2 is. But we do know that O1 is 120. So this whole thing is a revolution. So I can say O2 is equal to 360 minus O1, which is 120, because this is a revolution, which is equal to 360 degrees. Okay, so O2 will be 300 minus 100 is 200, so it'll be 240 degrees. Okay, so that will be O2, 240. All right, now again, remember your angle at center, angle at circumference. So I can say, therefore, Y must be 240 divided by 2, right? Because it's half the size angle. So we're going to write in the bracket here, angle at center equals 2 angle at circumference. All right, so Y is equal to 120 degrees. So there we've got 120. Okay, now we still need to calculate X, and this is where this piece of information is useful. ABCD is a cyclic quadrilateral, and we know one of the properties is that the opposite angles are supplementary. So we know they add up to 180. So therefore we can say, example 2, prove that ABCD is a cyclic quad and determine Y. Alright, so remember, you have three options for proving that something is a cyclic quad. And here they are. You can prove that the opposite angles are supplementary. You can prove that the exterior angle equals the interior opposite, or that the chord subtends equal angles. Okay, now you may be tempted to have a look at something to do with exterior angles because you have one. However, I don't see any information about the interior opposite, so maybe not. You also have a lot of subtended lines here, which is probably the direction you should go in. Also because you have a diameter that is subtending the angles. So if you can recall, what was that little rule about the diameter? What angle does the diameter subtend? The diameter always subtends a 90-degree angle. So we know that C1 is definitely 90 degrees because of the diameter. You also notice that this diameter subtends B2. So we know B2 is definitely a right angle. Now do you notice that you've proved that two of these angles are equal? And what was one of my methods? One of my methods to prove was to prove that two subtended angles are equal, and then you will know for sure that it is a cyclic quad. Okay, so let's go and write that in. So we say B2, angle B2 is equal to 90 degrees because why? What is the reason for your diameter 1? We call it angles in a semicircle. Alright, then we can do the same thing, with C2. It's equal to 90 because angles in a semicircle. Right? Okay, so therefore, angle B2 is equal to angle C2 is equal to 90. So now you can say, therefore, ABCD is a cyclic quad. Okay, what is the reason? How did we prove it? Angles in same segment are equal. These angles in the same segment are equal. Okay, so therefore it is a cyclic quad. Now they still want us to determine why. They want that angle. Okay, so now that you know angle B2, we know angle B2 is 90. This is an exterior angle. We know that it's equal to the interior opposite. If we could maybe find out this whole angle, we could say y is equal to angle B. We know this piece 2. Is there any way to find out piece number 1? Well, if you look at CD, you can see it subtends. Oh, that was terrible. It subtends angle 10. So it also subtends angle B1. So we know, B1 is equal to 10 because angles in same segment. Correct? So we know that this is 10 and we know that that's 90. So what is the whole of angle B? It must be 90 plus 10, which is 100. Correct? So now that we know that angle B is 100, we can say therefore angle Y is equal to 100. Why? Because exterior angle of a cyclic quad. Remember, it equals the interior opposite. So this Y is equal to that whole B. Okay, I hope that makes sense, grade 11s.